All right, so today we're going to talk about Taylor series, and Taylor series are very closely related to Taylor polynomials that we've covered before. So let's remind ourselves what a Taylor polynomial is. So remember, a Taylor polynomial is a Taylor polynomial to approximate a function f of x centered at x equals c is, and then we give it right here. So that was what a Taylor polynomial is, but notice it's got a finite number of terms. And so the term Taylor series is typically used to refer to the infinite sum. So same exact thing, except this time n is infinite. So that's what we're going to be dealing with. And then this is the Taylor series centered at x equals c. All right. So before we get started, I'm going to put on the screen here several useful formulas that you should memorize for the AP exam and also for my tests. And then we'll take a look at those. All right, so these three are definitely good to know. I'm actually going to give you guys a sheet later on with just kind of like a cheat sheet of a whole bunch of stuff to know for the AP exam. But related to this, these are good to know. And then I'm going to put one more formula. It's not a, well, yeah, actually. It's a formula we looked at last time. Sorry, I was thinking about something else. And this is the one we did last time. So this is another good one to know. Your homework is actually going to involve more, but the book has them listed. Don't worry about memorizing them. So in your book on page 599, there is a table with more formulas to memorize. We're not going to derive these. You can go back and look at your notes. You can see where they came from. Let me just write this down. Table. More Taylor series. So, like if we look at the formula for e to the x, notice it's an equal sign now, because when we go to infinity, when we write down an infinite number of terms, now we actually have the same thing as e to the x. It converges, and it converges to e to the x. And then another thing to note is this right here, the one that's in terms of n, this is what we call the general term of the series. So here's the first four terms, here's the general term, here's the equation in summation form. All right, so what are we going to do with this stuff? All right, well, let's take a look. Oh, sorry. Okay, so for example, one thing we can do here, we can derive the Taylor series for sine of x using the Taylor series for cosine of x and vice versa. So this is more just to kind of play with it and see what we can do. You could derive the formula by using what we've done in the past, finding the derivatives and, excuse me, plugging in c equals 0 and doing all the stuff we've done before. But another thing that we can do, let's just start with the Sine X formula. So we know that sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. I would keep this on until we get to the summation. We can write this as -1 to the nth power x to the power of 2n plus 1 over 2n plus 1 factorial as n goes from 0 to infinity. So starting with this guy, what I can do is take the derivative. And we know the derivative of sine is cosine, so I can take the derivative to derive the formula for cosine. So let's see what happens. I take the derivative of sine x, which means I can take the derivative of every single one of these terms. Which means I can also take the derivative of this series, which is really what I'm doing. So how does this work? Well, derivative of sine, we know that that's cosine. That's nothing exciting. And then I just take the derivative of each one of these terms like I normally do. So the derivative of x is 1. The derivative of this guy right here, this x cubed over 3 factorial, that is going to be 3x squared over 3 factorial. And then I'll have plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus da-da-da-da-da. And I'm going to hold off on the other thing, but we can simplify this a little bit because there's a 3 as a factor on the top and a 3 as a factor on the bottom. When I cancel out the 3's, I'm left with 2 factorial on the bottom. And then the 5's cancel out. So I have x to the 4th over 4 factorial. And then the 7's cancel out. And I have x to the 6th over 6 factorial. And oh my gosh, it works. That's actually cosine x. So that's exciting. But let's see what happens when we take the derivative of the summation. You just take the derivative using our derivative rules. So let me write this down. So negative 1 to the n doesn't depend on x. That acts like a constant, so that stays the same. But then the fractional part, I just do the power rule for derivatives. So multiply by the exponent, and then decrease the exponent by 1, and then the bottom is basically a constant. But just like what was happening in each one of the terms, I have that common factor in the numerator and denominator that's going to cancel out. 2n plus 1's cancel out. I'm left with x to the 2n over 2n factorial. Oh, well, look at that. It's cosine. So that's another way you can derive these formulas. Once you know one, you can use derivatives to go ahead and derive other formulas. So this did say vice versa, so let's go the other way. Let's see what happens when we go the other way. So now I'm going to start with cosine, take the derivative, and get sine. So I actually have cosine up there. I'm going to switch colors, though, just to make it clear we're doing something different. So I'm going to start with this formula. Whoops. And n goes from 0 to infinity. All right, so take the derivative. And I got kind of 3 parts to this equation, so I'm going to take the derivative of all 3 parts. I'm going to take the derivative of cosine. And I'm going to take the derivative of this hot mess right here. It's not really a hot mess, just a lot of stuff. And then I'm going to take the derivative of the sigma. Okay, derivative of cosine, we know that that's negative sine. And that's no big deal. We can multiply through by a negative to get a positive sign. We know that. I'll take the derivative term by term. Derivative of 1 is 0. I'm not going to write that down. Derivative of the next term is going to be negative 2x over 2 factorial. And then we're going to have 4x cubed over 4 factorial. And then negative 6x to the 5th over 5 factorial. And then over here, again, the negative 1 to the nth power is not dependent on x. So multiply through by the exponent decrease the exponent by 1, and then, oops, wait a minute. That bottom part doesn't change yet. So I have that, and then finally, when I simplify everything, the 2's cancel out, the 4's cancel out. I forgot my negative. Hang on one second. Sorry about that. Okay, the 2's cancel out. I'm just going to write minus x. The 4's cancel out, so I have x cubed over 3 factorial. The 6's cancel out. Oh boy, sorry guys. That should be 6 factorial there, but then the 6's cancel out. And over here, n goes from 0 to infinity, negative 1 to the n. The 2 n's cancel out. And now I have 2n minus 1 factorial on the bottom. Except I'm looking at this. There's something a little off here. This didn't work out quite like it did up above. Because look what's happening over here. When n equals 0, sure, that's going to be positive, but we're starting negative. And wait a minute, when n is 0, this is x to the negative 1 power. And then I have a negative 1 factorial. Wait, what? So some weird stuff happened. Big problem here. Can't take the factorial of a negative. So this didn't work. I mean, it appeared to. If you don't look at the sigma, the other stuff could work out. But we ran into problems with the summation part. Let's try integrating. So I'll go back to pink. All right, so starting back here with cosine x. And I'm just going to go ahead and go to the sigma part. We're going to save a little time here. So I have this, x to the 2n over 2n factorial as n goes from 0 to infinity. Okay, so taking the antiderivative of both sides, let's see what happens. I'm going to make a little note. Take the antiderivative of both sides. Antiderivative of cosine, that's sine. Over here, I'm going to start with that. And then we know to take the antiderivative, you add 1 to the exponent and divide by the exponent. So I'm still going to have this 2n factorial on the bottom, but I'm going to add 1 to the exponent and then divide by that exponent. Excuse me. And so then when we do that, then it's going to work out beautifully. Because on the bottom, I have the factorial part. So it's 1 times 2 times 3 times 4 times 5, all the way up to 2n. And then I'm going up 1 further to 2n plus 1. So I can just write that as 2n plus 1 factorial. And that worked. Yay! So you can play around with these and have, a little bit of fun. Back up here, we really could have done just some slight adjustments here and gotten a summation that could work. But we had to play around with that, so that was a problem. Like doing term by term by term, this was actually working. Over here we ran into a little bit. And so you kind of fudge things with the lower limits and do stuff like that. But regardless, this time integrals worked. So the whole purpose of that was just to see we can kind of play around with these things like that. We can manipulate them. Now, once we know some basic ones, we can also use them to derive other things. So here's another quick example. And this one's quick. I guess it's not really another quick example. It's just a quick one because the last one wasn't quick. But if I want to determine a power series for the sine of x squared, I could go through the whole, like, find a first derivative, find a second derivative, find a third derivative, find a fourth derivative. I'm going to center it at x equals 0. So then I could plug in 0 into the function and the first derivative and the second derivative and the third derivative and look for patterns and things like that. Or a much easier way to do it is this. Start with the one that we know. The sine of x is, and you know, it all kind of depends on how you want it. If you want it in expanded form, you can write it in expanded form. If you want it in summation form, you can write it in summation form. But start with the sine x expansion. And then we're just going to replace all of these x's with x squared. So that means sine of x squared is equal to x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial dot dot dot, which is the summation as n goes from 0 to infinity of negative 1 to the n times x squared to the 2n plus 1 all over 2n plus 1 factorial. And then all we got to do is just simplify a little bit. We can't simplify a whole lot, but I can simplify these numerators. And then I have x to the 4n plus 2. It's all over 2n plus 1 factorial. Ta-da! So much easier than trying to derive it from scratch. Use something known and play with it. All right, so another quick problem, just to kind of show you something else we can do with these, and then we'll get into something a little more meaty, is let's let a polynomial p of x equals 4 minus x minus 2 plus 3 times x minus 2 squared minus 5 times x minus 2 cubed be a Taylor polynomial. It's not a series because it stops, of degree 3 for f of x centered at x equals 2. Okay, so that's given. So the first part, can you find the second derivative evaluated at 2 hidden in this problem? And that's not too hard. So we got to look at the squared term, the term with degree 2, because we're looking at second derivative. And if you think of the formula for Taylor polynomials, we have this guy right here. Actually, if I'm going to generalize it, the nth derivative evaluated at c over n factorial times x minus c to the n. This is the coefficient in front of the x minus c to the nth power. So we're dealing with the second derivative. Excuse me. So the second derivative evaluated at 2 over 2 factorial, in this case, is equal to 3. Just multiply both sides by 2, and we get the second derivative evaluated at 2 is 6. So that's nothing special. And this really isn't that much of a big deal either. What if I want to approximate the derivative of 2.1 using a second degree polynomial? What are we going to do there? Well, so I know the given part. I know that the function is approximately equal to, because remember the polynomial is just an approximation. So the function is approximately equal to that polynomial above. That means that the derivative, and well, I should say that this approximation is good for x relatively close to x equals 2, because that's what I'm centered at. But 2.1 is pretty close to 2, so then I can say that the first derivative then is approximately equal to, and I'll take the derivative of everything. So derivative of 4 is 0. The derivative of x minus 2 is 1, so I'm going to have negative 1. Then I'm going to have 6 times x minus 2 to the first power, and then minus 15 times x minus 2 squared. There's my second degree polynomial, so all I got to do now is plug in. So the first derivative, evaluated at 2.1, is approximately equal to, and I just let all those x's equal 2.1. And then you can evaluate it. So the first derivative, you could put it into a calculator, but let's see. That's going to be 0.1, and then 15 times 0.1 squared. Ugh, the pressure of trying to do this right the first time. We got 0.6 minus 0.15. I don't know. We could do that arithmetic and you get it. Let's see. That'd be negative 0.4, so negative 0.55. So there we go. There's something else. Okay, so one more problem. This one will be a little longer. I'm going to start a fresh page for this one. See if we can fit it on one page. Okay, here's the problem. We're going to express the definite integral and I'm going to give it to you as an infinite series and find its value to within an error of at most 10 to the negative fourth. And the integral is the integral from 0 to 1 of the inverse tangent of x squared dx. So it's a definite integral. It's going to be area under this curve. But how do we take the antiderivative of that? Well, we don't have to. we can use Taylor polynomials or Taylor series to help us out. So from that table, from page 599, this is one you don't have to memorize, but we can look it up on a table and we can find out that the tan inverse of x is equal to this series. The summation as n goes from 0 to infinity of -1 to the nth times x to the 2n plus 1 over 2n plus 1 for these values of x. And then that means, now I'm dealing with the tan inverse of x squared, so if I let all of the x's equal x squared, I can get to here, that the tan inverse of x squared is equal to the summation as n goes from 0 to infinity of -1 to the nth, and then x squared to the 2n plus 1 over 2n plus 1, and this is true for the values -1 less than x squared less than or equal to 1. And this is going to be okay. We're going to be able to use it for this definite integral, because if you look at the limits, we're talking about values of x from 0 to 1. That would work in this interval. We don't have to worry about simplifying this interval down. We could. So we're going to be able to use this to help us out. So now let's see how we use it. Well, I'm dealing with a definite integral, so I'm going to take the definite integral of both sides. It's a little weird to have the definite integral with a sigma, but the idea still holds, and really I should put a dx at the end of each one of these. Make me happy. So we're going to integrate like we did before. We're going to have, excuse me, the integral as n goes from 0 to infinity of -1 to the nth. And then I'm going to do a little thing here with this guy right here. If I rewrite it, that would be x to the 4n plus 2. So then remember to integrate, you add 1 to the exponent and then divide by the exponent. So let me put these guys down. So if we have 4n plus 2, but we add 1 to the exponent, now we got 4n plus 3, and then we divide by the exponent. But remember, it's a definite integral. We are evaluating from 0 to 1. And then we actually plug in 0 and 1 into our x. So it's a summation as n goes from 0 to infinity of -1 to the nth, 1 to the 4n plus 3 over 2n plus 1 times 4n plus 3 minus the summation as n goes from 0 to infinity of -1 to the nth times 0 to the 4n plus 3 over 2n plus 1, 4n plus 3. So I just plugged in upper limit into x, lower limit into x. And then we can do a little simplifying here. This first one, -1 to any power, is going to be 1. We know that -1 to the power of infinity is going to be indeterminate. So you may be thinking, wait a minute, we're going to infinity, so wouldn't this be 1 to the power of infinity? But it wouldn't be. It'd be 1, we'd have to look at it term by term. It'd be 1 to the power of, and n equals 1, and then 1 to the power of, and you plug in n equals 2, and 1 to the power of. So we just never stop plugging it in. But we're always going to have, when we're evaluating this, we're always going to have some value of 1. So we can assume that's 1. And so we have the summation as n goes from 0 to infinity of -1 to the nth over 2n plus 1, 4n plus 3. And then with the second sigma, that's 0 to any power. And as long as we're never evaluating 0 to the power of 0, which we're not going to for these values of n, that's going to be 0. We're just going to be adding a bunch of zeros. We don't need it. So there it is. The first part of our problem is answered. The first part was to express the definite integral as an infinite series, and we did. The definite integral from 0 to 1 of tan inverse x squared is this series. Dun, dun, dun. Oop. So that's the first part. Pretty straightforward. Now let's talk about error. Well, if you take a look at what we got here, so now I'm going to bring this up. It's an alternating series, and so we have our alternating series error bound. Remember that the alternating series error bound says that this would be true. The actual series, because now we're going to use this series to approximate the value of the integral. So this is the actual series. If I could do this to infinity, I could actually get the value of the integral, but I can't. So I'm going to use some partial sum to approximate it. And we know that the error is going to be less than or equal to the next term, looking at positive. And we want that to be less than or equal to 10 to the negative fourth. So we have to figure that out. We basically have to figure out what value of n is going to make this term less than or equal to 10 to the negative fourth. What's the biggest value of n I'm going to be able to put in here? Like, how far can I go but stay under here? So let's see what that means. So we know that a sub n, so I'm just looking at the positive part, so I'm going to ignore that negative 1 to the nth. My a sub n is this. So my a sub n plus 1 is, let's see here, that would be 2 times n plus 1, so 2n plus 2 plus 1 would be 2n plus 3. And then if I put n plus 1 in the second quantity, 4 times n plus 1 would be 4n plus 4, plus 3, 4n plus 7. So that's the n plus 1th term. And again, we want that to be less than or equal to 10 to the negative fourth. Now, there's different ways we can go about this. It's essentially kind of a guess and check, although with technology we can use like graphing calculators and stuff to help us figure out what a reasonable n is. And then one thing that I can do, I can flip both sides here and say just the denominator then. But if I'm going to flip it, remember the inequality flips too, and then 10 to the negative fourth would flip to 10 to the fourth. So let's see here. What can I do? So there's, like I said, there's different ways you can do a little guess and check or something and just see what reasonable n's are to start with. If we let n equal 33, then we will find that the value of this is, I believe if I wrote it down right, did it on the calculator already, 9,591, so close, but I want to get bigger than that. So the biggest value, n equals 34, the value of this is 10,153. And that's it. That gets me just over the 10 to the fourth. So that means that the 34th partial sum will approximate the value of the integral. That's the smallest partial sum that will approximate the definite integral. Whoops. To within 10 to the negative fourth. Ta-da! So that's it. That's going to be this in a nutshell. So have fun with your homework, and I hope you all have a good weekend. And if I don't see you around on Friday after school, I'll see you guys on Monday. Bye.